Hi there, thanks for clicking on and watching. Welcome to this video. Hopefully you've done so because you're sitting Maths Edexcel A level this summer and the applied paper 3 is on the 21st of June. This video I'm going to go through some more questions to help you revise and prepare for the mechanics section. So here is the advanced information, and looking at that top line, constant acceleration is when you've got your Suvat equations, but we've also got F equals ma and vectors in there. So maybe you've got some forces given in terms of vectors to deal with as well. Variable acceleration and the language of kinematics. So do you know when things come instantaneously to rest, your velocity is going to be zero. If there's a change in sign and velocity, then it's traveling in one direction, and that's at the point it will turn and go the other way. If things are displaced, that's the distance they are away from where they started. So just make sure you know and are aware of the different things that you can be asked and the language involved in motion with those types of questions. The projectiles and acceleration being constant, that's pretty general, lots of questions to practice there. The dynamics, usually things are moving, but then we've got equilibrium there as well. So you could have a question that involves both. And then the statics and the moments involving friction as well. So I'm going to go through one or two of each of these bullet points, but plenty of questions for you to find in the topic tests and then online in past papers too. So here's my question one. It involves constant acceleration, forces and vectors. We've got a mass, 3 kilograms moving under a constant force. T equals 0. Our U is going to be 3I minus 5J. 4 seconds later, we've got our V, and we're being asked to find the acceleration. So if we write down our Suvats of what we've got, we know U is 3 minus 5. 4 seconds later, V is minus 511. So the Suvat equation we're going to use is V is equal to U plus AT. So minus 511 is equal to 3 minus 5 plus 4A. Taking the initial velocity over, we're going to get minus 8 and 16 is equal to 4A. So A is going to be minus 2, 4. So put it in terms of I and J, we've got minus 2I plus 4J. Now we've been asked to find the magnitude of F. So we need to apply F equals ma. So F is going to be the mass, 3, times the acceleration, minus 2, 4. So that will be 3 times minus 2, minus 6, 12, and because we're asked the magnitude, we have to do 36 plus 144, just squaring both those components. The square root of 180 is 13.4 newtons. Now we're told at 6 seconds, P is at point A with position vector 6 minus 29, and at this point the force is removed and then it moves with constant velocity. 3 seconds after the force has been removed, then P is at point B and we're being asked to find the distance from the origin to B. So we need to know what the constant velocity is going to be, and that's going to be the velocity after the 6 seconds. So what is V at T equals 6? We can use that V is equal to U plus AT again. So V is equal to our initial velocity, which is still our 3 minus 5, plus 6 lots of the acceleration, which is minus 2, 4. So 3 minus 12 is going to be minus 9, and then minus 5 plus 24 is going to be 19. So this is the constant velocity it's going to then move with. So because we've now got constant velocity, if you think of a constant speed, it goes that many meters every second, and we want to know where we're going to be when we're traveling 3 seconds at this constant speed. but we're already at the point 6 minus 29. So the position is going to be 6 minus 29 plus 3 seconds worth of the constant velocity. And if we do that, 6 minus 27 minus 21 minus 29 and 3 lots of 19 is 28. And then we're trying to calculate the distance, so we need to again take the magnitude, so it's 21 squared plus 28 squared, and that comes out to be 35 meters. So this is a variable acceleration question. We've got a particle moving along the x-axis and its velocity equation is being given by this equation here. So we can see its variable acceleration when the velocity time graph and the equation is a straight line. The gradient of the velocity time graph is the acceleration. So when it's a straight line, the gradient's constant, and we can see here the velocity equation isn't a straight line, so we've got variable acceleration. So in part A, we're being asked to find the time when it's instantaneously at rest. That's going to be when velocity is equal to 0. So all we need to do is factorize that quadratic. So 3t and t, two numbers that times together to give plus 21. Signs are the same, but negatives involved. So we have a 3 there and a 7 there. And then all we need to do to find t1 and t2 is to solve those brackets. So T1 is going to be 7/3, T2 is going to be 3. So in part B, find the magnitude of the acceleration. So to find the acceleration, we need to differentiate. It's going to be dv by dt. It's the gradient of the velocity time graph. So differentiating, we're going to get 6t minus 16 and then find it at t is equal to 7/3. So that's going to be 6 times 7/3 minus 16, which is going to be 2 times 7, 14 minus 16 minus 2. Now being asked for the magnitude of the acceleration, so it doesn't matter that we've got a minus number, that it's slowing down, just the sheer size of it is the magnitude, so the acceleration is 2 meters per second squared. Now for part C, the distance travelled. If we think about the velocity time graph, so from t equals 0, we're going to get our quadratic that's going to come down like this. Now where we found where this has its roots and the velocity is equal to 0 was at 7/3 and 3, and we're trying to find the distance travelled. So when you have the velocity time graph, the distance travelled is the area under the curve. So we can see the area is going to be here below the curve, so we're going to expect to get a negative value. So what we need to do to find the distance is integrate between 7/3 and 3 of the velocity equation, 3t squared minus 16t plus 21 with respect to time. So that's going to be 3t cubed over 3 minus 16t squared over 2 plus 21t between 7/3 and 3. So putting our limits in, we can cancel first actually, and that will be 8. So this will be t cubed, 20 is 3, 27 minus 8 times t squared, which is 9, plus 21 times 3. Take our lower limit, 7/3 all cubed minus 8 times 7/3 plus 21 times 7/3. And if we do all that, we get in our calculators minus 4 over 27. So the distance travelled, we can ignore that minus. It's just going to be 4 over 27, which is equal to 0.148 to 3 significant figures, and that will be the distance travelled. Now for part D, show that P does not return to O. So if we think about the distance equation, which is our t cubed minus 8t squared plus 21t t. We can factor out a t, so we're going to get t squared minus 8t plus 21. And think about how we graph this. So it's going to be a positive cubic, so it's going to go up, wiggle up. It's going to go through the origin here. Now to find if we've got any more roots, we can do b squared minus 4ac and have a look at the discriminant of that quadratic inside the bracket. B squared is 64 minus 4 times 21, which is going to be minus 20. So we're not going to get any more roots where the graph is going to go through the x-axis. So it's going to go up, come down, and then go back up again. So these places here, if you think about differentiating the distance equation, we'll get velocity. And where did velocity equal to 0? That's the max and min here. So this is the 7/3 and the 3. So we're traveling away from where we've started, if this is distance against time, and this was up here v against time, but we can see we're traveling away. We start to come back. If this graph did have some roots and it went back down to here, then you could see this is traveling back to O, but because it doesn't come back to the x-axis, we can see that it does not return to O. Next is a projectile question. It's taken from the topic test. We've got two particles being projected and they collide. So a little bit more to think about than when one particle just gets projected. But we're given the information about P being projected at 20 meters per second at 30 degrees, but no information about Q. We're told that they're projected from A and B, which are 50 meters apart, and they collide 2 seconds after being projected. And for part A, we're being asked to find the velocity of P the instant before it collides with Q. So that's going to be when T is equal to 2 seconds. So let's resolve component form initially what's happening. So horizontally it's going to be 20 cos 30 and then vertically 20 sine 30. So if you know your exact values, your exact trig values, cos 30 is root 3 over 2. And so that's going to be cancelling the 20 and the 2, 10 root 3. Sine 30 is a half, 20 times a half is going to be 10. Now when you're doing projectiles, the horizontal component remains constant, but what will slow it down is gravity. So vertically it'll slow down. So it's going to project, and 2 seconds later it's going to have the same horizontal component but vertically, because what's slowing it down is gravity, and that's going to be constant, so we can use our suvat. So vertically V equals U plus AT, so V is going to be our 10, and then gravity is going to be minus G for 2 seconds minus 2G, so that's going to be minus 9.6. So that will be the vertical component. Now it's asking for the velocity, which is going to be the vector, so we can give it as those component forms, but when you're doing projectiles it gives you the vectors as the speed and the angle. So we can do that because at 2 seconds later we can make a triangle and try and find that angle. Now even though that says minus 9.6, the sheer size on this triangle is just 9.6, and then we've got our 10 root 3. So to find that angle with the horizontal, we can do tan to the minus 1 of 9.6 over 10 root 3, and that comes out to be 28.99, so 29 degrees, and that would be the angle that it is at 2 seconds later. But then what is the speed? The speed, we can just take the magnitude, so that's going to be 10 root 3 all squared using Pythagoras, 9.6 all squared, and if we do that, that comes out to be 19.8. So the velocity is going to be speed 19.8 meters per second at an angle of 29 degrees to the horizontal. Okay, part B, we're being asked to find the theta and mu for Q. So we don't have that. Now we need to find two unknowns, and what we're going to do is have two equations, one from the horizontal components and one from the vertical, and then solve them simultaneously. So resolving horizontally and vertically for Q, it's going to be U cos theta and U sine theta. They're going to be our initial. Now, when we look at the horizontal component, S1 being horizontally how far P travels and S2 how far Q travels, we know that S1 plus S2 is going to equal 50. Now, because horizontally the speeds are constant, we can just use our formula triangle that speed is distance over time. So the distance is just speed times time. So this is going to be 2 seconds times 10 root 3 plus 2 seconds times U cos theta is equal to 50. Divide throughout by 2. 10 root 3 plus U cos theta is 25. So U cos theta is 25 minus 10 root 3. So that is one equation in the two unknowns, and that was what we did horizontally. So now let's have a look at vertically. Now vertically, because we've got our constant acceleration, we can use our SUVATs. So S is equal to UT plus half AT squared. So for P, we can say that it's going to be UT, so that's going to be 10 times 2, so that's going to be 20 plus half G times 4, and then the vertical component for P is going to equal the vertical component for Q. So Q is going to be 2U sine theta plus half G times 4. So they're both equal. Now what we can do to both equations is take this half G times 4 off both and get that dividing by 2, 10 is equal to U sine theta. So these are our two equations. And what we can do, because we've got U sine theta and U cos theta, we can say that U sine theta over U cos theta, put in the relative parts of that on the other side, is going to be 10 over 25 minus 10 root 3. These u's will cancel, and we can do inverse tan because we've got sine over cos to get that theta is going to be 52.5. And then if you just put that back in to one of the equations, maybe this one is the easiest, 10 is equal to U sine of 52.5, and just divide through by sine, you'll get that U is 12.6. So that is U and theta. And then for part C, state one limitation. Well, you can say it's the size of the ball is not taken into account, the spin of the ball, or you can say any wind is not taken into account. So they're the limitations of the model to finish that question for part C. This is a question involving friction and an inclined slope, and we have got that the two blocks are joined by a light and extensible string. So light, so the weight doesn't need to be taken into account, and inextensible, so the acceleration is going to be the same throughout. It's on an inclined slope with alpha, and tan alpha is 5/12. So as soon as I see that sort of thing, I will put on a separate triangle that when we've got alpha and tan alpha being opposite over adjacent, by Pythagoras the hypotenuse will be 13, and then sine alpha is going to be 5 over 13, cos alpha is 12 over 13. Now if we put the forces on the diagram, we're going to have the weight 3 mg acting down. The tension, because it's joined to A, is going to be pulling it back. That same tension throughout is going to be what's carrying A up the slope. A's weight is going to act down 2 mg, and then if we resolve that, parallel and perpendicular to the slope, it's 2 mg cos alpha, and that angle there is alpha, and we've got 2 mg sine alpha. We've got the reaction here, and then because it's going to be going up the slope, we're going to have friction mu r opposing that motion. So what we need to do is apply F equals ma for both the blocks. So I'll do B first, that's the easier one. What's carrying it down when it's being released from rest, because it'll start to accelerate this way, will be 3 mg minus t is equal to 3 ma. And then doing the same for A, what's going to move it and which way is it going to move? It's going to move up the slope. T is going to take it up the slope, but it's got the weight component acting parallel to the slope, 2 mg sine alpha, and it's got the friction. The coefficient of friction mu is 2/3 and r is 2 mg cos alpha, and that's equal to 2 ma. Now tidying this up and putting in what sine and cos of alpha are, t minus 2 mg sine alpha is 5/13 minus 2 times 2, 4/3 mg cos alpha, which is 12 over 13 is equal to 2 ma. Tidying up even further, t minus 10 mg over 13 minus, now that 3 can cancel with that 12, and we'll get minus 16 mg over 13 is equal to 2 ma. Now we've got 10/13 mg minus 16/13 mg, so that's t minus 26 over 13 mg. 26 over 13 is 2, so it's t minus 2 mg is equal to 2 ma. Now bringing down the other equation, we've got 3 mg minus t is equal to 3 ma, so that's A's equation of motion and B's we can now solve simultaneously. Now because we've got T's the same but opposite signs, we're going to add the two equations. So minus 2 mg plus 3 mg is just going to be mg, but then adding on the right is 5 ma. M's will cancel and we'll get that g over 5 is equal to a. Now for part A we've got to show what t is. So going back to A's equation, t is going to equal 2ma plus 2mg. So that's going to be 2m times g over 5 plus 2mg. So 2/5 mg plus 2 whole mg. 2 whole mg in terms of fifths is 10/5 mg plus another 2. That is going to be 12 mg over 5. So just looking at part B and C, after B reaches the ground, A will continue to move until it comes to rest before reaching P. So what's going to happen? The whole thing is released from rest. The 3m is going to hit the ground. The string will then become slack, so the driving force that was taking A up the slope will go. It will continue to travel because it's already under motion but it will slow down because it's not got that driving force, and it tells us that it will come to rest before it reaches P. So before, when we had the equation for motion for A, applying F equals ma from before, we had T, the driving force, minus the weight component acting down the slope minus the friction, which was 16 over 13 mg, is equal to 2 ma. Now the driving force, the tension taking it up the slope, will go. It will continue to go up the slope, but when it comes to rest, the weight component is going to want to send it back down the slope, the 10 mg over 13. But now, because that weight component will be trying to send it down, instead of friction opposing the motion going up, friction, the mu r, will go in the opposite direction to try and oppose that motion, the weight acting down. So because the 10 mg over 13 is less than 16 over 13 mg, so the weight is less than the friction, F max will not be reached, so A will remain at rest. So that's part B. Part C suggests two refinements that would make it more realistic. Well, we had for the modelling purposes that the string was light and inextensible, so the string may have weight and be extensible. We might have friction at the pulley, and we've modelled A and B as particles, but they were blocks, so the blocks may have dimensions. So for 2 marks, you just need to say 2 of those to finish that question. Here we have a moments question. We've got a ladder resting in limiting equilibrium, so all the forces are going to be equal and opposite. The ladder is modelled as a uniform rod. We've got the ladder is length 6a and it's resting against a wall that is just 4a high, so we can see we've got an overhang at the top. The ladder is resting against a circular rail. Now usually when you have a ladder resting against a wall, the reaction from the wall is horizontal, perpendicular to the point of contact, but in this case the reaction at the rail will be perpendicular to the ladder, so it will go in that direction. Now we're told that sine alpha is 4/5, so whenever I see that sort of thing, I'll put a separate triangle and opposite over hypotenuse for sine. Pythagorean triple, the adjacent will be 3. So we already know that sine alpha is 4/5, so cos alpha will be 3/5. Now noticing from this triangle it's 4a high, if I just put an a in all the dimensions of that Pythagorean triple, Pythagoras' theorem will still work, and that's telling me that the length A to C is length 5a, so C to B, this overhang, must be A. So now let's put some forces on. Because it's uniform, we're going to have the mass of the ladder, which is mg, acting in the middle down, and we need to resolve that parallel and perpendicular to the slope. So here is my alpha. This will be mg cos alpha and mg sine alpha. Now there will be some forces acting at the ground. We'll have the reaction from the ground. Now because we're told it's in limiting equilibrium, F max will be reached, but the ladder will want to slip this way, so F max will oppose that motion, and it'll be mu times the reaction at the ground. And now what do we need to do in part A? Show that the magnitude of the force exerted on the ladder by the rail is 9 mg over 25. So if I do part A here, what we're going to do is take moments about A, because the forces that we don't know, the reaction at the ground and mu rg, the friction, we don't know those, but they won't affect the turning because they're actually at A where we're taking moments about. So the only forces that will affect the turning are those that are perpendicular to the ladder. So that's going to be mg cos alpha, which is going that way, and we've got the reaction at the rail. So when we're taking moments, it's the distance to that perpendicular force from where you're taking moments about. So because it's in the middle, it will be 3a mg cos alpha is equal to, how far is A to C? That was 5a times the reaction at the rail. Now we can cancel by A and feed in that we know that cos alpha is 3/5, and then all we need to do is tidy up and cross multiply. 9 mg over 25 is equal to the reaction at the rail, which is what we're trying to find in part A. Now in part B, hence or otherwise, find the value of mu. Now mu is involved in this force that is horizontal. So instead of working now parallel and perpendicular, we're going to work horizontal and vertical. So the reaction at the rail will need to resolve in the two components. So that is going to be this way and this way. So where is my alpha? I can see by alternate angles, here will be alpha. Then in the right angle here, this will complement to 90. And then I can see that will be the same as that complement to 90. So here must be my alpha. So this vertical component will be the reaction of the rail, the size of it, cos alpha. And then at the top, we've got the reaction at the rail, sine alpha. Now I've got all my forces, and I will do the horizontal ones first. So the horizontal ones are equal and opposite. Where are my horizontal forces? I've got the friction, which is mu rg is equal to the reaction at the rail, sine alpha, which is the size of it, which I worked out in A, 9 mg over 25 times 4/5, which is equal to 36 mg over 125. Now if I do the vertical, forces up equals forces down. So which the forces going up and down? We've got the reaction at the ground going up, and we've got the vertical component from the reaction at the rail. They're both going upwards. So you've got Rg plus the reaction at the rail, cos alpha, is equal to mg going down. So Rg plus the reaction at the rail is our 9 mg over 25 times cos alpha, which is 3/5, is equal to mg. So Rg is going to be mg take away 27 mg over 125. Now if you think you've got a whole mg minus that fraction of mg, so that's going to come to 98 mg over 125, and then all we need to do is feed that in here for our Rg, the reaction at the ground, to get that mu Rg is going to equal 36 mg over 125. That was our equation from the horizontal forces. So mu is going to be 36 mg over 125 divided by 98 mg over 125. We can see the 125s will cancel, the mg's will cancel. This will give us 36 over 98, which cancels down to 18 over 49, which is mu. Thanks so much for watching, everyone. If you're still with me at this point, do like and subscribe. Check out my other videos. Best of luck for all your revision and your exams next week, and I will see you on the next one.